Hi, my name is Jeff Larkin. I'm a software architect in NVIDIA's HPC software team where I work on HPC programming models. And today I want to talk to you about using standard languages and the parallelism available in those standard languages for parallel programming. NVIDIA is a full platform company. We're best known for our GPUs. However, last year we announced our intent to build the Grace CPU for data centers, and we also have our networking component through our acquisition of Mellanox InfiniBand. We need to provide a full, comprehensive way to program for every piece of this stack, whether it's for just the CPU or the GPU or the network or all of these pieces together. The foundation of this is our accelerated libraries. We have a rich set of accelerated libraries for math, for parallel algorithms, for communication, data analytics, AI, and more. On top of that foundation, we provide three different approaches for parallel programming. And today I'm going to be focusing primarily on this one on the far left, accelerated standard languages. What I mean by that is using a standard language like ISO C++, ISO Fortran, or Python, we can leverage the features that are already in that programming language to expose parallelism, and then build that application to run on multi-core CPUs or GPUs or whatever platform you're interested in. Here I have three examples. The first one using ISO C++, the parallel algorithms library to implement a Saxby algorithm, single precision A times X plus Y. In the middle, I've also written Saxby, this time in Fortran, using do concurrent, a feature that enables us to parallelize data parallel loops. And in Python, I'm showing the cuNumeric package, which aims to become a drop-in replacement for the ubiquitous NumPy package. And again, I'm writing a Saxby algorithm that can then be parallelized, run on CPUs or GPUs or whatever. By focusing on standard language parallelism, your application is parallel from the start. It's parallel first, which means no matter what platform you come to, you can expect to be able to build and run that application. We're seeing a lot of success from applications using these standard languages, and we encourage developers to start here. Now, as you develop your application in that way, you may find the need to incrementally optimize your code. And for incremental optimization, we do provide compiler directives through OpenACC and OpenMP. We've seen a huge amount of success in legacy codes using OpenACC. And we can also use OpenACC as a way to add small improvements to codes written in standard languages. And then on the far right is CUDA, in this case CUDA C++, but we also have CUDA Fortran. And this is where NVIDIA likes to innovate. We can expose new hardware features through the CUDA platform. We can expose new ideas in software as well. And if your goal is to get the absolute best possible performance on the GPU you have, the CUDA C++ and CUDA Fortran give you all of the tools you need to do that. And all of these approaches are fully composable and interoperable. And we've seen many codes that mix and match all of them together. So you can choose as a programmer how much you want to optimize for productivity and portability, or how much you want to optimize for a particular GPU. And we provide all of these approaches to you. So standard language parallelism, or accelerated standard languages, enable you to write your code once and expect it to run everywhere. And here I'm showing examples, again, in ISO C++, ISO Fortran, and Python, where this code can be built and run on a multi-core CPU. Here I'm using NVC++ or NV Fortran to build those codes. Or changing a compiler flag, I can run it on the GPU as well. I'm also showing the Python code here using the legate command in place of the Python interpreter, and I'm able to then specify how many CPUs or how many GPUs I wanted to even scale up beyond individual nodes to full systems. Using accelerated standard languages is not a new idea. This is something that we've been working with the community on for more than a decade. We have members of NVIDIA from all parts of the company. We've compiler engineers, application developers, hardware engineers, researchers who participate in these ISO languages because we believe that open standards are critical to developer success. Our compilers began to support accelerated standard languages in our 2020 releases, but even at that point, we had dedicated more than a decade to working in the language bodies to add features for parallels concurrency and working within our software and hardware stacks to be able to support those features when they came out. On the right, I've listed a variety of important major features that we've contributed to, and there's even more coming in the future. So let me talk first about parallel programming using ISO C++. ISO C++ began to support parallel programming in C++ 17 with the introduction of the Parallel Algorithms library. The Parallel Algorithms library provides you with basic building blocks that you can then use to build up your application. Things like standard transform, standard reduce, standard sort. These building blocks can be used and put together to build out a full application that supports parallelism out of the box. Now, C++ 17 also provided forward progress guarantees to ensure that your application won't deadlock, and also memory model clarifications to make sure it's safe to parallelize. And at the same time, we were developing our hardware to also support these same guarantees so that our hardware can support ISO C++ out of the box. C++ 20 also added several features that make the lives of parallel programmers better. C++ 23 is expected to be the next release of C++ coming next year, and it's currently in the final stages of standardization. It has a variety of features that we're really excited about, including MD-span, a way to represent multidimensional data natively in C++. Range-based parallel algorithms, which simplifies the use of these parallel algorithms across ranges of data, and extended floating point types, which have become important in a variety of application domains. But even C++ 23 isn't the final destination. We're continuing to work on future standards. Working on proposals for standardizing an interface to linear algebra, and also the senders and receivers framework, which enables you to specify asynchronicity in your code and also concurrency of different building blocks. This is going to really help with managing parallel work and being able to use all of the hardware that you have available to you. And I have an example of this later in the presentation. So to highlight what's possible today using C++, I'm going to start with a mini app called Lulesh. This is a hydrodynamics mini app from Lawrence Livermore National Laboratory in the United States. It's written in about 9,000 lines of C++, and there's a variety of parallel versions using MPI, OpenMP, OpenACC, and even CUDA. This is really designed to test out various programming models and the capabilities of the compilers. The code on the left is the baseline code as the application developers have written it. It uses OpenMP as its plan for parallelization, and you can see exactly the things you would expect from an OpenMP code. A parallel directive here, a for directive here, even some if-defs to make sure that we have a single source code that supports both serial and parallel execution properly. Now, we worked with the developers to take the code like this, and this is just one function out of many, and refactor it using only ISO C++, and here's the result on the right. You can see the code is much more compact, it's easier to read and maintain. And because it's fully ISO C++ standard, it's portable to any ISO C++ compiler. NVIDIA's NVC++, GNU's G++, Intel's ICPC, and many more. So this code, in addition to all of those advantages, it turns out that it's actually faster too. Here's some performance results. Here I'm comparing 3 different compilers on an AMD EPYC processor. You can see that the baseline OpenMP version the performance is fairly comparable among the three codes. Here I'm showing the default OpenMP parameters for each of these compilers, and as you tweak some of the environment variables, you can actually bring them to the point that they all have essentially the same performance. The next 4 bars are showing ISO C++ code without any OpenMP. And as you can see, on all 3 compilers on the exact same hardware are much faster than the original code. Here, G++ is roughly 2x over our baseline. Same thing with Intel's ICPC, and the NVC++ compiler is more than 2.7x faster than the original. Now, what's really impressive from this, though, is that using that same code completely unmodified, we can actually rebuild the code and run it on a A100 GPU and see even more of a performance benefit. So without any platform specialization, without any non-standard code, we can run across multiple compilers and multiple hardware platforms portably. Now, doing that with a mini app is one thing, but here I'm showing a full application. This is Maya, which comes from RWTH and Aachen University in Germany. This is a multi-physics package that has over 500,000 lines of code. Now, not all of this application has been refactored to use ISO C++ at this point, and the result I'm showing is from their Lattice-Boltzmann solver, that portion of the code. This portion of the code has been written using ISO C++, for on-node parallelism and MPI for inter-node parallelism. And you can see they're achieving great results. Compared to their baseline OpenMP code, the ISO C++ code is roughly the same speed, but has the added advantage that rebuilding the code, I can now run it on our A100 GPUs as well, completely unmodified. Now they took it a step further and they're using MPI to then scale upward, and you can see that they're actually getting fairly good strong scaling using only ISO C++ for offloading to the GPUs and MPI for scaling up to multiple GPUs and multiple nodes. So what's coming in C++? And the first feature I'll highlight is MD-span, which really makes the programming of multi-dimensional applications much simpler. The code on the left is what you would write today. Here I'm using standard span, but this could just be a flat C-style array as well. In here, when I go to index into this data, I need to calculate the offsets myself, which is messy and error-prone. Here, fortunately, this is only 2D data, but many scientific applications have 3D, 4D, 5D data, which makes this process expensive and error-prone. Now, you can do this with macros and simplify things a little bit, but MD-span actually provides a way baked into the language to handle this multidimensional data. So I declare that this MD-span, which is a view into the data, is an n by m array. And you could see down here inside of my parallel algorithm, I just index it as a two-dimensional data. So this will greatly simplify writing code that accesses multidimensional data and make it much less error-prone. Now, an upcoming C++ feature that we're even more excited about is the senders and receivers framework, also previously known as executors. Now, this is a feature that's not coming to C++ 23. It's actually being considered for C++ 26, but we're already actively working on a prototype of this feature. What we have here is a sample of a solver for Maxwell's equations, and we've written it to use the parallel algorithms and then the senders and receivers library that's coming in C++ 26, and this is a prototype library we have internally. You don't necessarily have to understand all of the syntax going on over here. What's happening is we're building out a dependency graph of how these different parts relate. So we move in the graph, and in the indentions here, we're chaining together dependencies, and then this pipe operation is another syntax for when this is done, call this, and then call this, so building out the dependencies. Nothing in here says anything about building the code to run on a CPU or on a GPU. I've used the parallel algorithms, and I've exposed the relationship between these parts, and then I'm going to use a scheduler to then determine how and where this code should run. And here's an example of how we use these schedulers. So up here is the only change I would make to that code is to this standard sync wait call. And the sync wait call says synchronize and wait for these Maxwell's equations solver to complete. And you can see I've passed in 3 different schedulers. The first one is the inline scheduler. And that kind of does what it sounds like. It does one thing after another in a sequential inline order. Now, I don't show that on the graphs here because the performance is so much slower that it kind of skews the graphs. Next is an OpenMP scheduler. It takes the work and schedules it to OpenMP threads. And you can see I have results here for 128 OpenMP threads and 256 OpenMP threads. And looking at the efficiency graph on the right, in this case 100% is full stream triad performance. You can see that both 128 threads and 256 threads achieve comparable level of efficiency compared to stream triad. Now I can also take that same code, now change the scheduler to do a CUDA scheduler that will map the parallelism to CUDA threads and CUDA devices, and you can see I can run on one A100 GPU or even 2 A100 GPUs without modifying the code at all. So I use the parallel algorithms as building blocks. I use senders and receivers to expose asynchrony and concurrency in my algorithm, and then I use the scheduler to portably schedule that to my hardware. Now in this slide, I'm taking the idea of senders and receivers and taking it to the next level. What I have here is a strong scaling plot where I've taken that Maxwell's equation solver and using a senders and receivers not just to scale to the GPUs on a single node, but actually up to over 1,000 GPUs on a DGX SuperPod. And you can see we can get close to 80% scaling efficiency, strong scaling up to over 1,000 GPUs using only senders and receivers. There's no explicit MPI, there's no explicit partitioning of the data. This is all handled by senders and receivers by exposing the relation of the parts of this algorithm. We're able to automatically scale it out to a full system scale. Now, this is very experimental at this point. We're a long way from this being released, but this does demonstrate our commitment to C++ 23 and 26 as we're developing these capabilities along with the language. And here we're using that same prototype on a real application. This comes from the Palabos framework, which uses computational fluid dynamics simulations using the lattice-Boltzmann method. And this illustration on the left was provided by Dr. Jonas Lott and Christian Huber from University of Geneva and Brown University, respectively, that demonstrates carbon sequestration in a porous media. So this code was ported or refactored to use the parallel algorithms, and then we've applied the senders and receivers library on top of that. And you can see scaling, in this case, strong scaling up to 512 GPUs using only the senders receivers framework. So we're committed to continuing to develop features, and as you can see, we're developing features that enable us to support C++ 23 as soon as possible. As soon as it's released, we plan to have full C++ 23 support as soon as possible after that, and we're already beginning to work on C++ 26, which is still several years off. So we're very committed to providing that support. Now, accelerated standard languages isn't limited to just ISO C++. We're also seeing great results with ISO Fortran. So Fortran introduced the do concurrent loop in 2008 and extended capabilities in 2018 and is continuing to extend capabilities in the next version, which we're expecting in 2023. Now, NVIDIA began to support automatically parallelizing and offloading features of the Fortran language with our 20.5 compiler. And at that point, we looked at operations written with array syntax and array math intrinsics, and began to offload those automatically to our GPUs. 6 months later, we released a compiler that could do the same thing with do concurrent loops. And so now we can take loops written in the form of do concurrent and parallelize them for multi-core CPUs or offload them to GPUs automatically. The Fortran language also has coarrays, which is a partitioned global address space programming model. You could think of it as an alternative to MPI if you'd like. We don't currently support this in our software stack, but it is something we're interested in supporting in the future. Now, I already hinted that do concurrent is getting an update in the next version of Fortran, which is currently called 202X. And that's the introduction of reductions on do concurrent loops. This is a feature that previously, if you wanted to run do concurrent loops, you need to pull out any reductions and call them separately. Now, do concurrent will have a reduce clause available to it. We've already begun implementing this and have it available in our compiler, and we know application developers that are already using this in their applications. So one application that we've seen using do concurrent is Miniweather. Miniweather is a CFD code that is meant to represent CFD as it's used in climate and weather applications. It is a member of the Spec HPC benchmark suite, and it's been written in a variety of different programming models. Here you can see I've taken one subroutine here and implemented it using do concurrent. If you're not familiar with the do concurrent syntax, this would be a triply nested do loop with standard Fortran do loops, and here I've put them together so that to inform the compiler that across all of the iterations of the LL, the K, and the I loops, these iterations can be run in any order, and so the compiler is free to parallelize them. You can see on the right that we're getting great performance. So the OpenMP code serves as the baseline on the CPU. Do concurrent on the CPU runs well too, although it is, in this case, slightly slower than the OpenMP code. It does have the advantage, however, that unmodified, you can run that same do concurrent code on a GPU. And it gets a huge speed up that is on par with the same code written using OpenACC. Pot3D is another application using do concurrent today. This is a Fortran application written for approximating solar coronal magnetic fields. It likewise is included in the Spec HPC benchmark suite. They had an existing code that used MPI and OpenACC. They decided they wanted to see what was possible using strictly do concurrent. Would it be possible then to use their application without any directives at all? So they rewrote the code. So their original code here, you can see this is units of time, so smaller is better. They took out all of the OpenACC except for a small exception for the atomic directive. They needed that in a couple loops. And you can see the performance was about 10% slower. So they're able to write their code essentially with no directives at all and get within 10% of their optimized OpenACC code. So that's already pretty good, but they wanted to understand what was causing this 10% slowdown. And after some experimentation, they discovered that because the do concurrent version uses CUDA managed memory to provide a unified memory space between the CPU and the GPU, if they use the same feature in OpenACC, they get essentially the same performance. So to them, that pointed to the use of managed memory as being the source of their slowdown. And so they went in and added back just enough OpenACC to control the data movement. So all of the parallelism comes from the Fortran language, and then they use OpenACC to incrementally optimize their data movement. And what they found is the performance then was essentially the same as the original OpenACC code, but with dramatically fewer directives and less code to maintain. So this demonstrates what I was saying at the very beginning of the talk, that you can begin with using accelerated standard languages and then incrementally optimize using directives if you would like. Now, do concurrent isn't the only feature of the Fortran language that enables parallel execution. Fortran also has a rich set of math intrinsics that can be applied to arrays. And here, as an example, you can write a matmul intrinsic, as I've shown here. Now, of course, someone could go and write the code on the left with triply nested do loops. I hope you won't, though. Instead, you should be writing this code on the right, which we can then map to our accelerated libraries and deliver great performance. And of course, the performance improves over time because you can count on us to provide the best possible math libraries for every generation of our hardware. So you can see as I moved from the V100 hardware to the A100 hardware, that the performance improved as you would expect. And this isn't limited to just matmul. There's a huge variety of array math intrinsics in the Fortran language that can automatically be parallelized and offloaded to our GPUs. Now, the final thing I want to talk about is the same notion of accelerated standard languages in Python. Python is not an ISO language like Fortran and C++. But the PyData ecosystem has become so ubiquitous in scientific computing that we believe we can accomplish similar goals in Python as well. So people write their code in Python because they want to accomplish high productivity. It's a very productive programming language, and you can see here on the left an example code. Nothing about this code tells you that it's a parallel code. It's actually written with standard sequential semantics. There's no visible parallelism. There's no synchronization. There's no partitioning of data to be able to run across multiple processors or multiple nodes. And it's also composable with all sorts of other libraries and data types. So you can plug this into your application and use it along with other Python libraries as well. So this is a really straightforward code, but despite how simple this code is, and despite the fact that it uses completely sequential semantics, you can make this code run on a supercomputer as well. We have a package we announced last year called cuNumeric. cuNumeric aims to become a drop-in replacement for NumPy, which is a ubiquitous member of the PyData ecosystem. So many packages NumPy that in some cases you may be using it not even realizing because it's used under the hood. cuNumeric transparently accelerates existing NumPy applications by replacing the NumPy data structures with data structures that can be partitioned and made parallel under the hood. So in many cases, you can actually take a NumPy application, change your import statement to import cuNumeric instead, and begin to run right away. So you can see here is an example from a CFD code that comes from Lorena Barba's CFD Python course. Nothing in here tells you that it's doing anything other than writing code in NumPy. On the left, or excuse me, on the right, you can see the application performance. The blue dot is CuPy. If all I wanted to do was take NumPy code and run it on a GPU, CuPy could already do this. What cuNumeric adds is the ability to then scale that outward. And here what we see is the problem size is increasing relative to the number of GPUs. And you can see we weak scale very well up to 1,024 GPUs using this simple code. So all we have to change is the problem size. And under the hood, the cuNumeric package using a package known as Legate under the hood is able to scale up to full machine scale. And how does it perform in general? Well, one example we have is this distributed join benchmark from the Rapids team. The Rapids team has a hand-optimized version of this benchmark that is roughly 1,700 lines of code that has CUDA in it and MPI, and everything has been hand-tuned to get the best possible performance. Now, obviously, I can't show this whole code in my slide, so I'll refer you to this version if you'd like to look. Now, the Python version of this benchmark can fit on the slide, and this is it. This is the entire code here. We use NumPy and we use pandas here, and under the hood, those two packages are using our Leagate framework. In terms of performance, this dark green line is the hand-coded version, and here we're running on fairly small time units here. And the bright green is using this Python version of the code, and you can see it's scaling fairly well, very comparably, and the runtime performance is pretty close. So in terms of productivity, it takes a lot less programmer effort to be able to write this code, which means when programmers have new ideas they want to go and try out, they can write this code very quickly and expect to get very good performance compared to the handwritten code, which will take much, much longer to develop. Now, as one more example, we took an example from scikit image of a Richardson-Lucy deconvolution. This implementation is based on NumPy, and it's available in the scikit image library. And we've changed it out to instead of using the NumPy package, we use cuNumeric instead. Now, one notable thing I'll point out here is that the convolve method in NumPy is limited to 1D arrays. cuNumeric actually supports convolutions across multi-dimensional arrays, and that actually results in a pretty significant performance improvement. So here are the performance results, up to 1,024 GPUs of a DGX SuperPod using A100s. In this case, we are increasing the problem size as we increase the number of GPUs, and you can see that the throughput is increasing commensurately. So we get very high throughput, increasing the number of GPUs with very little code change. So in conclusion, I do want to point you to a variety of GTC talks from a few weeks ago that give you more information about these topics. Several of them speak to C++, Fortran, and Python, as well as NVIDIA's HPC software stack in general. This from directives to do concurrent case study highlights the POT3D application that I mentioned earlier and goes into much greater detail. And I'll also point to this final one here from Simon McIntosh Smith and his group at the University of Bristol, which highlights some of the performance and portability they see using ISO C++ compared to CUDA versions of some of their applications. I also want to provide you with links to a variety of resources that you can use, including several application examples, some blog posts, and some references that you can use to begin developing using accelerated standard languages. So I want to thank you for your time. I hope that you're excited by what you've seen here, and that you'll begin to look into accelerated standard languages for your applications. And I encourage you, feel free to reach out to me, and I'd be happy to talk to you about these goals. Thank you.